NASA's Double Asteroid Redirection Test, known as DART, was the first real demonstration of asteroid deflection technology. The mission was designed to test whether a spacecraft could alter an asteroid's motion through kinetic impact. This was not science fiction or simulation. It was a full-scale planetary defense experiment. The goal was simple but unprecedented. For the first time, humanity attempted to change the orbit of a natural object in space. DART targeted a binary asteroid system millions of kilometers from Earth. The mission focused on measurement, not destruction. Success depended on precision, not power. The implications extended far beyond a single impact. Concerns about asteroid impacts have existed for decades. Scientists understood that large impacts could cause global damage. Early detection programs improved tracking but offered no solution. Avoidance alone was not enough. Active deflection became a serious topic. NASA began studying kinetic impact as a viable method. The concept relied on momentum transfer rather than explosives. Even small velocity changes could accumulate over time. Long warning periods were critical. This approach was considered realistic and scalable. The DART mission was approved in 2017. It was designed as a technology demonstration, not an emergency response. The goal was to gather real data. The mission would test predictions made by models. Results would inform future defense planning. A binary asteroid system was selected as the target. Didymos and its smaller moonlet Dimorphos provided ideal conditions. Any orbital change would be measurable. The system posed no threat to Earth. This ensured safety during testing. Dimorphos became the primary target. Its orbit around Didymos was well understood. A change in its period could be detected from Earth. This made it perfect for evaluation. Precision measurement was essential. The mission emphasized simplicity and reliability. DART carried no scientific instruments beyond navigation and guidance. The spacecraft itself was the experiment. Impact was the only required outcome. Everything depended on accuracy. DART was a relatively small spacecraft. It had a mass of about 610 kilograms at launch. Simplicity reduced risk and cost. The design prioritized autonomy. Human intervention would be impossible during impact. Power came from large deployable solar arrays. These used rollout solar array technology. The arrays provided sufficient energy for propulsion and navigation. This technology was also being tested for future missions. Efficiency was critical. Propulsion was provided by ion thrusters. These engines offered high efficiency but low thrust. They were ideal for long-duration deep space travel. Maneuvers were gradual and precise. Fuel consumption was minimal. Navigation relied on an autonomous optical system called SmartNav. The spacecraft tracked Dimorphos visually. This allowed real-time targeting without ground control. Autonomous guidance was essential due to communication delays. The system performed beyond expectations. DART carried a single camera for navigation. This camera also transmitted images back to Earth. Scientists used these images to monitor approach accuracy. The camera remained operational until impact. Data transmission ended seconds before collision. Didymos is a near-Earth asteroid system. It consists of a primary body and a smaller moonlet. Dimorphos orbits the larger asteroid. The system is well characterized. This made it ideal for study. Dimorphos is approximately 160 meters in diameter. Its size made it representative of potential threat objects. Objects of this scale could cause regional devastation. Understanding deflection at this scale was crucial. Larger bodies would require more time. The orbital period of Dimorphos was known precisely. It completed one orbit every 11 hours and 55 minutes. Even small changes could be detected. Ground-based telescopes were prepared. Timing accuracy was vital. The system was located about 11 million kilometers from Earth at impact. This distance ensured zero risk. Observations could still be conducted effectively. The location allowed clear tracking. International observatories participated. The binary nature of the system simplified measurement. Changes in Dimorphos' orbit were isolated. Effects on Didymos were negligible. This separation reduced uncertainty. Data clarity was improved. The target selection ensured scientific confidence. Predictions could be tested directly. Models could be validated or corrected. This was the mission's core purpose. Accuracy mattered more than spectacle. DART impacted Dimorphos on September 26, 2022, at approximately 6.6 kilometers per second. The spacecraft used only kinetic energy. No explosives were involved. Impact occurred precisely as planned after months of navigation. Observers on Earth and in orbit tracked the approach. Every aspect of the collision was recorded for analysis. The collision produced a large debris plume, visible from telescopes. Material ejected from the surface enhanced momentum transfer. Observers noted the bright flash and cloud of dust. The effect exceeded initial predictions in some models. Scientists immediately began analyzing data in real time. Measurements showed Dimorphos' orbital period shortened by about 33 minutes. This surpassed mission requirements. The result confirmed that kinetic impact can deflect an asteroid. Momentum enhancement due to ejecta was critical. The mission validated theoretical models conclusively. The impact demonstrated that human technology can alter natural orbits. DART proved a concept previously only imagined in simulations. The experiment provided insight into asteroid composition and surface response. Future planetary defense missions would use this data. Control over potential threats became more feasible. International cooperation was a key part of the mission. Observatories and space agencies shared real-time data. Model predictions were updated collaboratively. Lessons learned improved global understanding of kinetic impact. Scientific engagement reached unprecedented levels. DART's success also highlighted challenges for larger asteroids. Scaling up would require greater energy and precision. Different surface compositions could alter effectiveness. Mission planning must account for these variables. The results provided a benchmark for future missions. The experiment marked a turning point in planetary defense. Humanity moved from theory to practical capability. Knowledge gained will guide subsequent missions. Confidence in kinetic deflection increased dramatically. Planetary protection is now more than just a concept. DART fundamentally changed the field of planetary defense. For the first time, a spacecraft successfully altered the motion of an asteroid. Predictions were replaced by measurements, giving scientists reliable data. The experiment proved that human intervention in orbit is possible. The mission set a precedent for future planetary protection initiatives. The spacecraft's autonomous navigation was a major success. SmartNav tracked Dimorphos visually and executed precise adjustments. No ground intervention was needed during the final approach. This demonstrated that autonomous control is viable in deep space. Future missions will rely heavily on similar systems. Follow-up missions, including ESA's Hera, were immediately planned. Hera will study the impact site and measure long-term effects. Observations will refine models of momentum transfer. Data will inform the design of larger deflection missions. DART laid the groundwork for these operations. Public awareness of planetary defense increased significantly. The mission showed that threats can be mitigated proactively. Media coverage highlighted the technology's potential. Engagement inspired interest in space science. Humanity witnessed a real-world demonstration of defense in action. DART proved the technology is scalable given sufficient warning. Smaller asteroids require less energy to deflect. Late detection limits options drastically. Lessons emphasize early detection as critical. Detection and deflection are inseparable components of planetary defense. While DART was not a weapon, it had strategic implications. The ability to control asteroid trajectories became realistic. Ethical and international governance discussions intensified. Collaboration is essential for safe implementation. Responsibility in space became a key consideration. DART stands as a turning point for humanity's approach to planetary threats. It transformed a theoretical concept into practical reality. Future missions will build upon its success. The experiment validated kinetic impact as a viable defense. Planetary defense is no longer hypothetical. It is achievable.